What's up, folks? Little DJ Shadow for you to kick it in. So we changed gears now from a lot of sound stuff, particularly standing waves on strings and air columns. We switched gears now to, well, a fundamental property of waves, reflection, and how that helps us figure out things like images, where images are formed by mirrors. All right, we'll start with the simplest case, what we call a plane mirror or a flat mirror, and we'll move into curved mirrors, all right, like those, like funhouse sort of mirrors, okay? So there's two main kinds of ways that waves can reflect, specifically light. Come here, there you go. Specifically light. And light can reflect in a way that we call specular reflection, you see here on the left, and that happens off of nice, smooth surfaces. And then there's diffuse reflection, which happens over rougher surfaces. So, I will say that the reason you can see anything at all is because light reflects off of it and hits you right in the eyeball. All right? And for most surfaces, even though they don't look like it, they're pretty rough. All right? So even though light comes off and sort of bounces in all directions, lots of different directions, some of those directions happen to be happen to hit you right in the eyeball, okay? So you won't see an image of like a light bulb when you look at it. I'm looking at a chalkboard right now. I don't see the light bulb's image in there because the light doesn't bounce off in a nice orderly fashion like you see here. It bounces off all over the place. And only some of those rays will hit me in the eyeball, all right? If we use a mirror like this, that's a nice smooth surface, and we get this nice specular reflection, we can see the image, of a light bulb, say, that bounced, where that made that light that bounced off the light bulb, or bounced off the mirror. Okay, so most of the things we see are diffuse reflection, but we're going to spend the most of our time talking about images formed with specular reflection. Okay, well, I don't know. Yeah, I guess back to reflection. We did talk about reflection, and when waves hit boundaries, all waves hit boundaries, the wave can, at least part of the wave can bounce or will bounce off that boundary or reflect off it. All right, so if we look at an incident wave, incident means incoming, a wave that is incident upon this boundary, and, well, what it'll do is it'll bounce off and go like that. Okay, now we're looking at what we call wave fronts here, right? Remember, if this is a wave front, then here is a wavelength. And coming out here is a wavelength. So wavelength stays the same in this case, but what we have to, now I can show you an applet about this, but maybe easier just for now to sort of take my word for it. Hopefully it sort of makes sense. This is what we call a ray, right? A ray is a real simple way to talk about a wave or to demonstrate the direction that a wave is going. We don't care so much here. When we draw rays, we don't really care about wavelength, but what we do care about is what direction the wave goes. The wave comes in like this, where we say it's incident upon the boundary like that, and then it's reflected like this. All right? The law of reflection says, well, this thing is called a normal, and a normal is a line drawn perpendicular to a boundary. Boundary right where a ray hits it. Right? If we look at this normal, and you're going to draw normals for all sorts of anything we do in what we call physical optics or geometric optics, we're going to use normals. I'll show you why it becomes more important in our next little look when light goes through boundaries. But anyways, if we look at, the law of reflection says that this angle here, which we call theta incident, and this angle here, which we call theta reflected, those are the same. That's the law of reflection. Theta incident, that's too big. I'll do it like this. Theta incident equals theta reflected. Or you'll just see it as theta I equals theta R. Right? That's the law of reflection. Simple as that. Hopefully that sort of, you're able to, accept that empirically without much evidence. Okay? What else is there to say there? Big deal. Angles, whenever we do optic stuff, angles are always measured from a horizontal. Okay? Okay. Now, if we want to find the image of an object in a plane mirror, what I kind of wish I did, screw it. Let's find the image of this object. All right, here's a mirror. Right there. Right? Here's an object over here. We always draw objects as arrows. Right? And the reason we do that is so we can see when the image is formed, is the image upright, looking the same as the object, or is it inverted upside down? That's why we use arrows. All right, so we're going to find the image of this object. And to do it, we're going to do what we call some ray diagramming. Now you will need a ruler here, and ideally a ruler and a protractor. I wish I had said that earlier, but I didn't. So if you have a ruler and a protractor, great time to go get it. Ready, go. Okay, now that you have your ruler and protractor, here's what we can do. Like we said, the reason, when you look in a mirror, the reason you can see yourself is because light bounces off of you. There's lights above your mirror, maybe in your bathroom, or if you're in your room and you have a mirror in there, there's a light, in the ceiling somewhere. And light, there's light that's hitting you, and some of that light bounces off of you and happens to go towards the mirror. Well, that light that bounces off you and goes towards the mirror then can bounce off the mirror and come back and hit you in the eyeballs. All right, and that's how you see yourself, because light comes off of you, bounces off the mirror, comes back and hits you in the face, in the eyes. All right, so we can kind of draw that. Even though there are, an infinite number of rays of light that come off of you, here's an interesting one. Here's one that makes sense for us to look at. And those are your eyes, let's just say. We'll put them right at the top of your head. You're a strange-looking person. Light comes, in this case, off, the top of this arrow. And this light that's incident right along the normal. Remember, the normal is a perpendicular to that mirror. Well, if it goes in like that, I don't know if you can see, but we said that the light goes in this way and then bounces right back and comes back that way, because the incident angle and the reflected angle here are both 0. All right, let's take another ray and say draw it like this. It doesn't have to be to the very bottom of the mirror. We just chose to make it go there. All right, well, that light is going to hit this mirror here, and it's going to bounce off like that. Of course, we have to, here's where you really need a protractor. We have to make sure that we don't just draw any old reflected ray. We have to make sure that these two angles are the same angle. That's the law of reflection. All right, we could draw any other rays we wanted. Pick one that goes like this if you want. Do I have one of those? No. That one that comes in, well, we would draw it like that. Then we could say, okay, let me construct a normal, a perpendicular, right? Measure that angle. This thing bounces out at the same angle like that. As long as those angles are the same, we can look at any of the rays that come off the top of that arrow. All right, well, where's the image of this arrow, or the top of the arrow? Where's the image? Well, we have these rays that have reflected off the mirror and come out this way, and come out this way, and come out this way. So where's the image formed? Well, the big deal is that the image is formed where the rays converge. Well, the problem is this, and this are never going to converge. They're never going to come together. So we add this, or where they appear to have originated. Now these appear like they might have originated somewhere back here. We trace that one back, we trace this one back, and even if we traced this one back, tricky freehand, oh yeah, no coincidence, these rays all look like they originated at the same place. And therefore, that's where the image of the top of that arrow is. Oh, now notice, I'm doing, that tells us where the image of the top is. The image of the top is right here. If we want to figure out where the image of the bottom is, look, I'll do the same thing. Ray going in, ray coming back. Any other old ray hits the mirror, bounces off, again, such that those two angles are the same. They have to be the same. And we know that this ray here coming out here and this ray here coming out here are never going to converge out on the left, so we trace them back and we look where it seems like they came from. It seems like they came from right here. So here's where the image of the bottom is. Here's where the image of the top is. Connect the dots. There's our image. Fair enough? Things to notice about the image. What do you notice about the image? Sorry, I'm just trying to see what comes up here. Oh, good question. Things to notice. One, we say the image is upright as opposed to inverted. Not inverted, right? The arrow points up. 2, well, what we can call the object, the distance to the object, and the image, same thing. Okay? Object distance and image distance, same exact distance. And we would say here that, well, there's no real variable for the size of the object or the size of the image, but we can say magnification. Well, it's not magnified. It's not smaller, it's not bigger, so we say that it has a magnification of 1. No smaller, no bigger. Right? Smaller means its magnification could be like 0.5. Bigger means it could be like 2. All right, but if it's 1, same size. Fair enough? Now, one question for you I'd like you to think about is this. Lots of us have full-length mirrors in our homes. You should try to figure out, I mean, you can just do this. I recommend you get a roll of masking tape and I don't know, maybe a meter stick or something, and you look at yourself in the mirror and you figure out what's the smallest mirror you can use to see the image of your whole body, right? Full-length mirror, the whole point is to see your whole body, right? I have a full-length mirror on the back of my closet door, and it's like, I don't know, 4 feet tall or something like that. And the question is, do I need that whole 4-foot mirror? Do I need more than that? Do I need less than that? How big is the smallest mirror you can use to see the image of your whole body? All right? I challenge you, make up a little experiment and figure that answer out. Okay? Now, a thing I want you to do today before you leave is the following. Here's an arrow. Here's a mirror. I want you to find the image of that arrow. Now, your gut, I hope, tells you, well, the image, the mirror image, better look something, whoops, a little too big, but better look something like that, right? Certainly not that long, but better look something like that. But as opposed to just, whoops, sorry, that way, of course. As opposed to just sketching it, let's do some ray diagramming to actually find the image of the arrow. You will definitely need a ruler and a protractor for this. You already have it. So here's how I would do it, right? Pick any old arbitrary ray from the top. draw it like that. It hits the mirror. All right, well, at what angle does it hit the mirror? Well, it's got to reflect at the same angle, right? There's the law of reflection. You actually have to do it twice for each end of the arrow. So here's any other old arbitrary angle or ray that comes off the tip, right? Hits the mirror there. Well, at what angle? Well, it's going to reflect at the same angle, all right? And we can say that, well, the image of that tip is formed where those rays seem to have originated. It's formed over here. Do the same thing for the tail of the arrow. Again, totally arbitrary, the direction of these rays. It does not matter. Pick one, draw your normal, and hey, don't just sketch the normal with the ruler. I mean, use a ruler. Use a protractor. All right, use a protractor. Make sure you are using a 90-degree angle. All right, don't just eyeball it. And let's see, this thing bounces off at the same angle. Pick some other angle, or some other ray, excuse me. Hits there, reflects like that. Trace these babies back. There's where the other end is, and oh yeah, look, perfect mirror image. All right, it's kind of easy to do this using PowerPoint because you can make sure you're flipping things perfectly and blah blah blah. If you're careful with a ruler and a protractor, specifically with the protractor, if you're careful, and use a nice sharp pencil, all right, you'll come out with a pretty darn good mirror image. Okay, so that's your job. Finish this while you're here, and I forgot that you're listening to this on Friday in class, aren't you? Yep, you are. And so I think good exercise here. Draw me the image of this object, and good exercise to answer before you go. Good question to try to answer here. I actually think I have a handout that you should have that helps you answer this. Okay? All right, folks. Happy Friday. There will be another video that you'll see for Monday. Okay? All right, folks. Happy Friday. Again, sleep.